Masood has to do this. I think I can't do this for some reason. Yeah, I don't have this option. Okay, there you go.
Okay.
Okay, so 25 plus 5, no?
Okay. Do you see my slides?
Very good. We can see it.
Okay. Okay.
We can also see the title of your talk. Then please go ahead.
Okay. First, I would like to thank the organizer for this opportunity. For this presentation, I'm going to talk about the magnetic field in heavy ion collision, and more specifically, I will talk about the interaction of the magnetic moment of the constituent particle with this magnetic field, which results as a finite magnetization in the medium. I'm interested how does this magnetization affects the evolution of the plasma. With this in mind, I'm starting with the generation of the magnetic field at the earliest stage of the collision. In relativistic heavy ion collision, charged particles are moving with relativistic velocities, and because of this, we can expect that an enormous magnetic field is to be generated orthogonal to the reaction plane. The magnitude of this magnetic field is approximately 10 to the 19 Gauss, and the major part of this magnetic field is produced by the spectators. So as these spectators leaves the interaction zone, we may expect that the magnetic field decays very fast. In such collisions, also the colliding nuclei carry a large angular momentum, and some part of this angular momentum remains in the interaction zone. This magnetic field and angular momentum may have some non-trivial effects on the evolution and dynamic of the plasma. But here, I'm just considering the magnetic field and ignoring the effect of the angular momentum. One thing I just forgot is that the magnitude of this angular momentum is approximately 10 to the 6 h-bar, which comparing to the spin of the particles is really large angular momentum. To simulate and study the behavior of the magnetic field at the earliest stage, people mainly use the linear Ricard potentials, which relate the electromagnetic field at the time t to the information of the phase space information of the particles at this retarded time. Here I'm just showing some plots based on the simulation based on those potentials. As you can see in the most central collisions, because two colliding nuclei cancel each other's contribution to the magnetic field is equal to the 0, but due to some event by event fluctuation, the magnetic field can be generated. The black dots correspond to the magnetic field, event average magnetic field along the y direction, and the red square correspond to the event average of the absolute value of the magnetic field in the y direction. As we increase the impact parameter, magnetic field starts to grow linearly, almost linearly with the impact parameter, and for the most peripheral collisions, when we increase the impact parameter, the magnetic field starts to decrease. In such collisions, other components of the magnetic field, like the X components, can be generated, as well as the components of the electric field due to the event-by-event fluctuations. The other plot shows the behavior of the magnetic field as a parameter, as energy increases. As you can see, at the LHC energy, the magnetic field increases linearly with energy, and at the LHC energies, the magnetic field is 10 times stronger than the magnetic field at top peak energies. At the bottom, plot, I'm showing you the space distribution of the magnetic field. This one is the X component, and the middle one is the Y component. As you can see, the magnetic field in the transverse plane is highly inhomogeneous, and this inhomogeneity can cause some problem, which I will talk about it in a few slides later. As as I said before, the major part of this magnetic field is being produced by the spectators, and when these spectators leaves the interaction zone, magnetic field starts to decay. The lifetime due to the spectators is approximately the radius of the nuclei over the Lorentz factor, which takes this value for typical energy for the typical nuclei. And when the spectators leaves the interaction zone, the remnant particle in the interaction zone dominates and causes the fields decay slowly. And as you can see, this can produce also the Z component of the magnetic field. If the medium has a finite conductivity, the whole picture may change and magnetic field may survive longer. This gives the motivation to study the effect of the magnetic field on a variety of fields. For example, people started to study the effect of the magnetic field on the thermodynamic of the quark metal, and they found out that the magnetic field can play a role of the catalyzer to break the chiral symmetry. And also people started to study the effect of magnetic field on the dilepton production rate or the photon emissions, or its effect on the elliptic or directed flow. But one of the most interesting part is that you can use the magnetic field to probe the chiral medium and investigate the anomalous transport properties. Another interesting part is related to the spin polarization, which observed at heavy ion colliders, and magnetic field can provide a possible solution for this splitting observed between the polarization of the lambda and lambda bar. As you can see in this figure at left, the global polarization of the lambda hyperons along the direction of the global angular momentum is observed, and it takes a small but non-zero values. And there is a difference, a small difference between the polarization of the lambda and lambda bar. Some people believe that this difference is caused by the magnetic field, and if we believe that the major part is made by the magnetic field, we can put some constraint on the magnitude and the lifetime of the magnetic field. In this study, people used the difference between the polarization of the lambda and lambda bar to put constraint and an upper bound on the magnitude of the magnetic field at this energy. As you can see, they found that the magnetic field at the freeze-out surface should be smaller than the 10 to the -3 times the Parnell's mass square. In another study, these people tried different profile of the magnetic field, and they wanted, one of the aim of this study was to find the good fit for the lifetime of the magnetic field as a function of the energy. You can see the numerical value of this quantity, and if you compare it with the numerical value I showed you before here, you can see this is really this numerical value is increased relative to that that one, which may be a good signal that the medium effects increase the lifetime of the magnetic field. So lambda polarization may provide a good information about the late stage magnetic field, about the magnitude and lifetime. And based on some studies like this, if the medium has a finite conductivity, the behavior of the magnetic field mostly affected at the late stage. So at the one hand, the lambda are good tools to probe the later stage magnetic field strength, and the magnetic field at those times are mostly affected by the effect of the finite conductivity. So the late stage magnetic field, the lambda may provide also a good hint about the conductivity of the medium. But this is not the only way to study the effect of the interaction, to study the interaction between magnetic field and the spin of the particles. As you know from the quantum mechanics, when a particle with a spin, for example, an electron, moves in a non-uniform magnetic field, it feels a force, and this force deflects the particles and causes the separation of the spin up and spin downs. This force is proportional to the gradients of the magnetic field. In analogy, when you have a medium with finite magnetization, and you have a non-uniform magnetic field, this medium feels an anisotropic force, which again is proportional to the gradient of the magnetic field. This anisotropic force can change the geometry of the matter and reflects its effect on the elliptic flow. This effect is known as a paramagnetic squeezing. So our aim is to understand how the magnetization affects the behavior of the fluid. And because in a classical limit, working with varying magnetic field is more easier than at the quantum level, we want to know if we can do anything at the classical level. But there is a problem. When you use a statistical mechanic and classical mechanic together, the thermal average of the magnetic moment, which is the magnetization of the medium, is always equal to the 0. So the question is, how can we model the effect of the magnetization effectively? To do this, we look at the energy momentum tensor of the fluid. The total energy momentum tensor for system is defined in this way. The first two terms defines the ideal energy momentum tensor, and the last two terms are the energy momentum tensor of the electromagnetic part. These two extra terms include the effect of the polarization tensor. This polarization tensor M includes the effects of the magnetization and also the effect of the electric polarization. This auxiliary field is defined with the field strength tensor and the polarization. In the case of the infinite conductivity, the electric field is vanishing, and the electric field is vanishing, and we can look at the first part of the energy momentum tensor. This decomposition is not unique, but for the rest of this talk, I'm just considering this decomposition. As you can see in the vanishing electric field, this auxiliary field is equal to the 0, and the first part of the energy momentum tensor in the local rest frame is given in this form. For this configuration, when the system expands in the y direction and the magnetic field is aligned in the z direction. You can see there is a difference between the pressure of the system. There is an anisotropy in the pressure of the system, which is caused by the magnetization. In the transport theory, the energy momentum tensor is defined as the second moment of the distribution function. This is for the massless case. If we want to include the mass, we have to put the energy instead of the K here. For the anisotropic distribution function, we always end up with the zero magnetization. And if we have some sort of anisotropy on the left-hand side, we should have the corresponding anisotropy on the right-hand side. And this is the part we use the idea of the anisotropic hydrodynamic to introduce anisotropic distribution function with the help of this second rank tensor. This parameter is called the anisotropy parameter, and this 4 vector is the 4 vector that determines the direction of the anisotropy. In our case, this is correspond to the direction of the magnetic field. And there is also some correction to this form of the distribution function. With the help of this distribution function, we could study the evolution of the system under the Bjorken expansion and could read the evolution of the anisotropy parameter for 2 cases of the dissipative and non-dissipative. The blue line correspond to the non-dissipative and the black one correspond to the dissipative case. And also the effective temperature of the system, and compare it with the case that when the magnetization is equal to the 0 and the temperature change evolves according to the Bjorken. As you can see, at the earliest stages, the temperature for the anisotropic case drops faster, decrease faster than the case of the Bjorken, but the late time behavior is almost same. And I want to draw your attention to the behavior of the magnetic susceptibility. As you can see, when the system decrease the anisotropy parameter, the magnetic susceptibility start to increase. And when the system start to go to the isotropic case, the magnetic susceptibility start to decay. But the question is, how can we study the effect of the magnetization from the first principle and systematically? In classical transport theory, we use the distribution function to gain the information about the system, and the evolution of this distribution function is governed by the Boltzmann equation. This is the form of the Boltzmann equation in external force. If we want to add the information about spin degrees of freedom and also about its interaction with the background magnetic field, we need to extend this notion. And one way to do this is using the Wigner function formalism. A Wigner function is defined by the help of the Wigner operator. It's the ensemble average of the Wigner operator. And Wigner operator is defined for a fermionic system, is defined with the help of the fermionic field located at 2 different points. And there is a Wilson line, this guy, to ensure the gauge invariance of this quantity. And finally, taking the Fourier transport of with respect to the relative coordinate. For the case of the uniform magnetic field, we can find the decomposition of the psi in terms of the positive and negative frequencies mode. As you can see, the wave function is expressed in terms of the spin projection along the direction of the magnetic field and opposite direction of the magnetic field. For the lowest Landau level, this quantity pi is equal to the 0, So for lowest Landau level, we have only one spin degrees of freedom, but for higher Landau levels, we have both spin degrees of freedom. This decomposition is written for the positive charge. If we change the negative, we want the decomposition for the negative charge, this may need some changes. Also, there is a four momentum defined here, which its definition is given here. The first index in the K tilde is referring to the charge of the particle, and the second index referring to the the second index referring to the frequency or negative frequencies mode. So with the help of the Wigner function, we can find the energy momentum tensor of the system, and the 0,0 components gives the energy density, and the spatial components gives the pressure of the system. As you can see, there is a difference between the pressure along the direction of the magnetic field and those orthogonal to the direction of the magnetic field. I also want to emphasize that this coefficient here, alpha, which is defined in this form, takes into account the effects of the spin degeneracy factor. For the lowest Landau level, it's equal to the 1, and for higher Landau level, it's equal to the 2. We calculated these integrals into regime of the high and low temperature expansion, and substituting the energy and the different components of the energy momentum tensor in the energy equation, we could study the evolution of the temperature. The right panel corresponds to the high temperature expansion, and the left plots correspond to the low temperature expansion. As you can see, at the earliest stages, the temperature decrease very fast relative to the case of the zero magnetic field, but the late time behavior and evolution of the temperature is different for high temperature and low temperature. For low temperature expansion, the temperature keeps decreasing faster than the case of the magnetic field, but it's not the case for the high temperature expansion. With this, I'm going to finish the talk. Thank you for your attention.
Yeah, thank you very much, Ali, for this very nice presentation. So I have seen that there are a few questions here. I will start with Mujib Hassan. Can you switch on your camera and ask your question, please? There he is.
Hello?
Okay.
Can you hear me?
Yeah, it's a little low. If you speak loud.
Okay. So I want to ask that is this magnetic field is only generated for non-central heavy ion collision? So can you go your slide number 4?
Sorry, I couldn't hear your question.
Yes, this slide.
Okay.
So can you tell that why there is a finite value of magnetic field for impact factor B equal to 0?
This finite value is because of the event by event fluctuation. If you take the event average, it's equal to the 0, but if you take the absolute value of the average, the absolute value of the magnetic field, it's not 0. It's only because of the fluctuations.
Okay.
Very good. Yeah. Then again, a question by Yogesh. Yogesh, do you hear us now? And can you ask the question?
Asked that since we assume that a huge magnetic field produced at RIC and LSC, so what would be the expected value of generated current which is produced due to the heavy ion collisions?
Excuse me, what is the value of current?
The current, yes.
Electric current?
Because as we know, the charge, because of the charge, there is a current, and then this huge magnetic field is produced. So I want to know the quantitative figure.
In our case, we didn't consider any current. We didn't have a chemical potential. If you mean considering the effect of the finite chemical potential.
Yeah, I think this is the correct answer. No? This is charge neutral then. But maybe somebody can correct me.
Yeah, I would like to know the that value of current. Yeah.
Yeah, that needs to be computed dynamically. No? A bit difficult.
Well, you can compute it first by just looking at the current from the incoming nuclei, right? Is to point like sources passing one another, but then the reaction of the medium depends on the conductivity, the electrical conductivity.
Okay, so I think Masood also wants to. Masood has several questions. Masood, you are the.
But the question was that in your second work, the Wigner function approach, you're assuming that that B is constant, yeah?
Yes, to derive this decomposition, we assume that it's constant, but we take a step forward and we divided this interval into the small parts segments, and we assume that at each part the magnetic field is constant, but its value can change according to some function. For example, based on the evolution of the magnetic field in the Bjorken case, this crust one is the case of the Bjorken, and we solved this equation, the energy equation, at each segment, and found the evolution of the temperature. This is, I'm not saying that this is the correct way of dealing with the dynamical magnetic field, just an attempt to consider what's the effect of dynamical magnetic field.
What did you assume for the time evolution of B there? Was there some specific form you took, or?
Yeah, we took several functions, several forms for the magnetic field, but this correspond to the Bjorken evolution of the magnetic field.
Yeah.
You can solve the.
Just found
one over
here
tau
and cheap one others.
So you say the case like 1 over tau, like this.
Yes.
The frozen flux. Okay.
Yes.
So we assume infinite conductivity.
Yes. In the whole work, I assume the infinite conductivity.
Okay, very good. Yeah. Okay, Masood, are all your questions answered? You had another one regarding the pi term, but.
Yeah, it was. I was just guessing that if you have this pi term,
here,
and you have Bjorken symmetries, I think even if you have electric field, you don't have it will vanish. Yeah, I don't know.
This pi in the local restaurant is something like E cross B, which is proportional to the pointing vector. So if you have the flow of the energy of the electromagnetic field, it's
you don't have E cross B in the Bjorken case. If you have E cross B, the Bjorken is going to change. Yeah.
Yeah.
Okay. Thank you.
If you are referring, okay.
Yeah. Okay, very good. Then do I see further questions? You can also raise your hands. I don't see any questions right now. Then let's thank Ali again. Thank you.
Thank you.
And let's come to the last talk of this first session by